In this video I'm going to talk about one sample Poisson hypothesis testing. So questions that you can answer with this kind of hypothesis testing is whether the rate of your population differs from some expected value. So an example of that is the rate of lung cancer higher than usual in my population? And just some review, a proportion or risk is the number of events over the total number of people. And that can let you say something like the proportion of people with cancer is 0.2. A rate, on the other hand, is the number of events over time, and it lets you say something about the incidence. So like the incidence of cancer is 4 cases per year. So to model rates, we use the Poisson distribution, and the y-axis here is the probability of a count, and along the x-axis here are counts. So 0 here is the probability of seeing 0 events, 1 is the probability of the event happening once, and 2 is the probability of it happening 2 times. So you can see that the mean here is about 3.4. That's the most likely number of events to happen over whatever the time span is. And yeah, you can see that as you exceed 3, it's not that these are impossible to happen, but the further you get from like the mean number of events, the less likely it is to have that happen like 13 times in a row, or 13 times rather than 3. And yeah, just some assumptions of Poisson. The mean of the Poisson distribution equals the variance, and that means that the variance here would be 3.4 in addition to the fact that the mean's 3.4. And another property is that as the mean increases, so here now the mean's 5.5, the distribution starts to approach binomial distribution. And the binomial distribution is like an example of that is if we have like a known probability of the event happening, like flipping a coin, then we can figure out the probability of getting heads like in a certain number of trials. So that's what you define for a binomial distribution: the number of trials, the probability of the event. And you can map, similar to this, the likelihood of getting like heads twice in your number of trials versus heads 5 times, and yeah, that would kind of like, let's just say it was 10 trials, you'd be likely to get heads 5 times most likely, because it's 50-50. But yeah, enough about the binomial distribution. Another property is that if the sample far exceeds like a low level, like 10 and beyond, it starts to approach normality. And that allows us, that's pretty important for hypothesis testing, just because as soon as you can assume a normal distribution, you have a lot more available to you. So like I said before, the denominator usually has some aspect of time in it, and what I'm gonna show here is just a concept called person time. I have a video on that in itself, where this is a group of people followed for 4 years, and yeah, it's the number of events is 2. Someone here had an event after 2 years, someone here had an event after 4 years, but instead of just saying like the raw rate being 2 events per 4 years, we're able to account for how much time each person contributed. So this person contributed 4 years, this person 2, 4 years, and 3 years. Yeah, and that comes out to 13 person years, so we're able to get a more exact rate. Yeah, so that brings us to another assumption of Poisson, which is that people are dropping out at random. So that means that those who dropped out prior to the end of the follow-up, this person dropped out without having the event, they were censored. Their risk of disease doesn't differ compared to those who stayed in. So yeah, a major assumption is that people are dropping out at random. Another is that disease risk is constant over time. So if it wasn't, like say all of a sudden the risk was higher here, this person's 2 years of contribution wouldn't be equal to this person's 2 years of person time contribution. So in order for this to work, we also need to assume that the risk of the event is constant over time. So as far as calculating incidence, it's represented by this term lambda, and it's just the number of events, the count over the person time of observation. So for example, if we had 700 events in a population followed for 10,000 person years, that would come out to 0.07 events per year, or 70 events per 1,000 person years. So yeah, if we have a question like, does the rate of lung cancer in our population exceed what's expected to a significant extent, now we're getting into hypothesis testing. So our observed rate is just represented by lambda. There should be a hat there. And the expected rate we're calling lambda naught. So the null hypothesis is that our population equals, the rate in ours equals the expected rate, and the alternative is that they're not equal. It can be above or below. And since time is equivalent in each of these, this is the same as saying that the number of events is the same in our population as the other population. So an example question, if a population is followed for 4,000 person years and 28 cases of lung cancer are observed, and we have an expected rate of lung cancer of 0.004 cases per year, is the rate of lung cancer significantly higher in our population? Just pulling information out of this, 28 cases of lung cancer were observed. The time of follow-up was 4,000 person years. The expected rate, lambda naught, is 0.004. So calculating our observed rate, we have a count of 28 over 4,000 person years, so 0.007. And just putting everything on a more reasonable scale, per 100 person years, that's just what I did there. So if we assume a Poisson distribution, then we can use this formula to construct a confidence interval. So just inputting the information we have a rate of 0.7. We assumed our Z alpha here. We're assuming alpha of 0.05, so it would be significant if p is less than 0.05. We put 1.96. Root y, we had 28 events, and t is 40 just because we scaled. And yeah, so it would be 0.7 plus minus 0.26. And if we do this confidence interval, we can see it comes out to 0.44 to 0.96. And we can see that our expected rate was 0.4. It doesn't lie in this interval. So although we don't have like a specific p-value, the fact that this null value is outside of our confidence interval, we know that it is at least qualitatively significantly different. Where if say it went below, like if it was like 3 point something to 0.96, then we wouldn't have confidence that our true value lies outside of 0.04. And yeah, we do in this case. But yeah, that's not as good as if we were able to assume a normal distribution, where as soon as the mean number of events exceeds 10, we can start to assume a normal distribution. So to do that, we're able to approximate it with a chi-squared statistic. So to start, we would figure out the expected mu naught. So our mu naught is 0.004, and we're following for 4,000 person years. Yeah. So our expected count would be 16, and then we would plug that into this chi-squared statistic. We witnessed 10, or we observed 28, we expected 16, So it would come out to a chi-squared statistic of 9. And now if we go to a chi-squared table, we can figure out what the critical value is. We have 1 degree of freedom and alpha of 0.05, so our critical value is 3.8, and our chi-squared value is 9, which far exceeds that. So that also is showing that our population is significantly different from the expected value. And the last thing, cumulative incidence, is a concept I just wanted to cover quickly that we're able to do. So if we're asked how many events one person is expected to experience over some time period t, if we have a really rare rate, so it's an uncommon event, you can figure out the expected number of events per person, by multiplying this rate by the time followed, and you'd end up with just y.